Today we're going to talk about Kung Fu. You remember that game? It was probably one of my favorite games, mostly because it's so addicting, but also I believe for its time, the game was pretty interesting as far as, characters and just kind of the mechanics. From a character perspective, I just remember as a kid, the coolest part of Kung Fu were the bosses. I mean, each boss had kind of their own personality. And, you had the stick guy, the boomerang guy, the big Mr. Clean guy with the deep voice. And then you had that black magic guy who was small and had a light voice, and you could knock his head off. I remember thinking that was super cool as a kid. I've always found this game to be really interesting. And the more I've kind of, looked into this game and kind of examined what makes it tick, the more I realize it is really interesting. So I was hoping to kind of spend a few minutes to dive into what makes some parts of this game work. Specifically, I want to look at collision boxes, hitboxes, and attack boxes. I feel like this code does a pretty good job kind of being very efficient with how they kind of draw the attack boxes. So yeah, if you're interested in that sort of thing, stick around and we'll have some fun. The first thing you need to notice is that Thomas is actually anchored at a specific exposition in the game. It's hard to notice this while you play, but if you take a look at the PPU viewer, the window on the right, he is literally anchored at a specific exposition, and that exposition is hex 80. I worked up this spreadsheet here. It's actually a representation of the Nintendo's display. Every single cell represents one pixel, and you can see here the numbers here at the bottom are hexadecimal numbers that represent the X position on the screen. Thomas is actually centered and always stays at hex 80. So I superimposed it here on the screen, but you can picture Thomas as one of those merry-go-round horses that have the poles sticking right through their body. And therefore when Thomas walks, it's actually like he's on a treadmill and the background is moving and the sprites are moving towards him, of course, so it looks like or gives the illusion that he's walking down the hall. Now, this is very important to remember for when we start building these hitboxes and these attack boxes, because it makes our programming that much easier if Thomas's expositions are always the same. When the knife thrower starts his action, the code stops right here. What they're doing right here is they're starting to build the attack box around the knife. So when the knife collision handler routine is called, meaning whenever the knife is on screen, every single frame, regardless of whether there's a collision or not, the code is copying and pasting the knife's X and Y position into the appropriate 0-page RAM location. From here, the code draws the knife's attack box into 0-page RAM. Here's how that works. So the basics behind any kind of a collision routine is to set a box. And if you think about what a box is, it's a, if you will, perimeter around a value. And to be able to draw any kind of a box, you have to have a base value, and then you have to have a distance between each, right? And those distances are given a name in programming. They're called an offset. Offset is kind of a catch-all phrase that applies to any value or the delta, if you will, between a base and a new value. So it's probably better if I show you a visual on this. So one of the interesting things I found when I started looking into this code is that the hitbox or the attack box for the knife actually is drawn 3 pixels to the right of the knife object itself. And the way we know that is this code down here. So you're loading the value that's in temp 10, which is the object X position. You're adding a value of 3 to it, which in this case is 3 pixels, and you're storing it in temp 0, which as you can see in the diagram, is the left side of the attack box. So yes, the attack box is actually leading the knife object here. So now that we found the left side of the attack box, which is the value that's stored in temp 0, all we have to do to get the right side is to simply take that value and add 2 pixels. So I know the diagram's not to scale, as you can see, but it should give you an idea of how this works. The knife attack box is 3 pixels in front of it and 2 pixels wide. Now that we have the left and right side of our attack box established, let's go ahead and focus on the top and the bottom. Now to do that, we have to peek inside temp 11, and that holds our object Y position. If you recall, the object Y position is updating and copying over to temp 11 every single frame that the knife is on screen. So we're going to take that value, which exists about 4 pixels above the knife object itself, and store that into temp 3. And to get the bottom of the attack box, you're going to go 3 pixels down from there and store into temp 1. So by way of a refresher, if you're looking at the dimensions of this box, the attack box of the knife is 2 pixels wide and 3 pixels tall. So when I started this, my goal was not to make this very long at all. My goal was also to not make this very complicated. It's kind of hard to be not complicated with computer code, but I did my best with visuals. I can't end here without first talking about Thomas's hitbox, right? And I'm going to move through that a little quicker due to time, and also because the concepts I use to describe the formation of the attack box actually are just the same as the code and the concepts used to form Thomas's hitbox. Because we know that Thomas's center is always hex 80, the math is pretty simple. So the offset here is, there's actually 2 offsets, okay? You're going to take the hex 80 and you're going to subtract, that's SBC, subtract 5 pixels. Okay, and that gets you the left side of the hitbox. That's going to be stored in temp 4. To get the right side, you're actually not going to waste a bunch of code and go back to 80. You're actually going to take the value that's already in the processor, which is the left side, and as opposed to adding 5 and adding 5 again, we're just going to add 10, and that's what that ADCOA is, and we're going to store that in temp 6. So in, what is that, 1, 2, 3, in 7 lines of code, we've established both the right and the left sides of Thomas's hitbox. Now, to establish Thomas's Y position on his hitbox, the top and the bottom, we actually have to do something we've not done before. We're not using math here. We're going to access values that are directly stored in the ROM. Because what these programmers did is a lot of times you could go in and you need to use variables and you need to use offsets to generate your values and your numbers. But sometimes, in this case, values are fixed. And you being the programmer, you actually can create data tables, literally type in data like you're typing into Excel or whatever, and just kind of paste them into the program file. So if you look down at the code, location BB94 and BB99 actually hold 2 specific and unique hard-coded values that the programmers literally sat there and typed in when they were writing this game. And those 2 values are the values we're going to use to establish the hitboxes. And those 2 unique values just happen to be value 92, which is the top position on the box, and value BD, which is the bottom. Now, this box is not the scale. If you were to look back in my spreadsheet, you'll see that the difference between 92 and BD is pretty much the entire length of Thomas, the entire height of Thomas. Because remember, we want to cover Thomas's entire body, because our knife thrower not only throws knives at Thomas's head, but he also can throw knives where? At Thomas's legs and feet. And so that hitbox needs to cover the entire length of Thomas, or the entire height of Thomas, if you will. So that just about covers the creation of the attack box and the creation of the hitbox. But I'd be remiss if I didn't at least touch on collision itself. Now, I'm going to flash this up on the screen, and the collision system here in Kung Fu, you're basically doing 2 things. You're comparing all the sides of the hitbox with all the sides of the attack box, and you're doing that for the X and the Y positions, or the horizontal and the vertical, or the top, bottom, left, right, however you want to say it. You're comparing side against side for every single dimension, and if you're doing that, you end up branching to a value of either 1 or 0, depending on whether or not there is a collision. So in this video, we covered the creation of the attack box when the knife object appears on screen, and we also covered the creation of Thomas's hitbox whenever he's being attacked. We glossed over the subroutine that covers the collision itself, but before we leave, I want to make sure that we understand branching. Now, it's a basic concept in all of programming, and in 6502, there are 4 branch instructions that are used more often than not. and they're definitely used in this subroutine and many other kind of collision check subroutines, and I'm going to flash them up real quick so you can see them. And just know, when you're building your collision routine, you want to make sure you're comparing all of the boxes with each other, okay? So you're comparing all those temp locations, and then you're doing very strategic branching. Now, there are plenty of resources online about branching, and all of those resources can cover them a lot better than I'm going to do now. But just know that we need to get very strategic with our branching when we're doing comparisons for collisions. And I believe personally, and you can feel free to agree or disagree, that this code does it very well. So that'll do it for today. I'll definitely be posting more videos on Kung Fu. Like I said earlier, I've taken a little bit of a deep dive into this game, and I want to share some other findings. There's some really cool things if we're developing our own Nintendo game for the indie market that we can take from this game. It's simple enough to where we can digest, but it's also complex enough to where we can do things very efficient in our games. So anyway, for now, appreciate your time, and I hope to see you next time.